Let me know when the screen is visible.
Yes, sir. Sir, it's
Yes,
It's
sir.
okay. So in unit 2, we are basically doing certain important distributions. We did discuss binomial and Poisson under the discrete ones, and uniform and normal distribution under the continuous random variable portion. And towards the end of the class, we did this transformation of random variable where given a relation of a random variable y with x and given the PDF of x, we are able to get the PDF of y using what we call as the conservation of probability. So we did one example, and I wanted to start today's class by giving at least one more example. So let's just consider that we have a random variable x which is distributed according to a uniform distribution between minus pi by 2 and pi by 2. So what will be PDF of this random variable? So A is minus pi by
1
2,
by
B
pi.
1 over pi, and it is between minus pi over
Minus
2
pi 2 to pi
less
by
than
2.
equal to x less than equal to pi by 2 and 0 otherwise. Right. And let y be a random variable which is related with this x using this function sin x. We want to find out the PDF of y. Now you see that I am writing capital Y as a subscript just to show that this PDF belongs to random variable y. So the question is in this form: x has a given or a known PDF, y's relation with x is given through sin x. We want to find out py or the PDF of y. So how are we going to find out? We use the relation which is written on the top. So what will be, let's say, dy over dx. This will be a simple cos x, but I want to write it in terms of y. So, if I want to write it in terms of y, how will I write it? This cos x.
Under root 1
so
minus
under
y
root 1
square.
minus y square.
Okay, cos x is equal to plus minus under root 1 minus sin square x, right? I mean, it is plus minus. But
Yes, sir, plus minus.
since we are going to take only the absolute part dy dx, so we will retain which one? Only the plus one. So this will be 1 minus sine square x, or basically 1 minus y square. So let's just do this simple one. So py over y then becomes px g inverse x. So this is 1 over pi, and there is no x term, so I do not need to convert into y. And then this is divided by 1 over root 1 minus y square. So the PDF of y, which is related with x through sin x, is as simple as that. But this is not yet done. What is the range of y? Range of minus pi by 2 to pi by 2. So what is the range of y?
Minus 1 to 1.
So sine of minus pi by 2 to sine of pi by 2, which means minus y less than equal to y less than equal to 1 and 0 otherwise. So this
Sir,
conservation, yes.
sir, why do we have the less than equal to? Wouldn't minus 1 equal to give us 0 in the denominator?
Yeah, so this is something which we do need to figure out. I totally agree with you that writing here is strictly equal to 1 will create problem in this y square root 1 minus y square. So use this and 0 otherwise. Otherwise, this PDF will blow up at y. This is the problem which you are facing, right? This is you are
Yes,
pointing
sir.
out, right? Yeah, yeah, it does make sense. In fact, this is the same thing for y equal to positive plus 1 also. So yeah, I mean, just put, maybe I should write once again. But this is the way we get PDF of a random variable which is linked with another random variable. Okay. So before coming up with something else, let me just ask one more question which we have been dealing with. So let's say we know that there exists a random variable with mean mu x and variance sigma x square. And let's say we know that there exists another random variable which is linked with this random variable. If I want to find out E of y and I want to find out variance of y, so these two terms, what will be these? So E of y is nothing but mu of y, and variance of y is nothing but sigma square of y. So if one variable is associated with another, a and b being constants, so what will be expectation value of y?
A mu plus B.
A of mu x plus b, right? This was simple. What about the variance of y relation with variance of x? So how do we get it? We get it by doing this. E of y minus ey square, right? So then you can try to open it in terms of x. E of, now what is y? Y is ax plus b. And what is E of y? That you have found out to be a mu x minus b. So what happens to b? This guy will cancel out. And we are left with E of
A sigma x square.
a square x, very nice, mu x square. Now expectation value of a constant time this term. That means that we will have a square expectation value of x minus mu x square, which is nothing but a square sigma x square. Now this gives one interesting property of the relation between the random variable. The random variable y, which I built from x, has one term a times x. A is generally called scaling, that you are scaling the random variable x by this amount a. And b is called shift. So these random variables, the a being the scaling one and b is shifting. Expectation value wise, if you found out there, since we know how the constant behaves, so it is just the a mu x plus b, doesn't take much of the time. But variance, the spread about the mean, that when you find out, you figure out that just shifting the random variable does not affect the variance. So if the random variable is shifted by some amount, then it does not get affected in terms of the variance. However, if the random variable is scaled, then the variance turns out to be a square times sigma x square. In fact, you can also write sigma y with sigma x, where sigma y is the standard deviation. What will be this?
A times sigma x.
The only thing which you will have to be careful about, that sigma y is the standard deviation, which is always positive. A being a constant, you do not know whether it was a positive or a negative number. So generally, just try to write down mod A times sigma x. Sigma x being a standard deviation is always positive. So this is just to know that. Why this is so important? Since the random variables are pretty useful in calculating random errors, so the shifting and the scaling properties, they matter in terms of the errors also. So errors scale just like the way the original random variable is. Now this is something which you might be seeing when you are again doing this counting statistics experiment, that if there is the number of count which turns out to be n, and you get the error in it, which is sigma n to be root n. So if I scale this number n by an, what would be corresponding error in this? This is something which is generally asked. Fine. So please see that you are able to do problems like this, and this can be done just by doing the simple standard deviation. Okay. So what did I want to start with in today's class? Today I wanted to do something about the bivariate distributions. Now, thus far, what we were doing falls under the category of univariate distributions, where we had one random variable and we tried to figure out the PDF, the expectation values, the variances of that random variable. Now we extend our reach to bivariate. That means we start talking about two random variables, x, y. And then it can be extended further to trivariate and multivariate ones, which goes to x, y, z, x, y, z, w, so on and so forth. The good thing about the bivariate distribution, once you know about the major items related with bivariate distribution, it can be very simply extended to multivariate distributions. So bivariate is kind of the most important one and the simplest one among the multivariate one, because this can be simply extended. So we will have to start from the basic point. We will have to define our PDF or the PMF. I am going to write mostly about the PDF, but wherever required, you please convert it into PMFs by replacing the integration sign by the summation sign. Okay. So in the case of bivariate distribution, we talk about Pxy or simply put Pxy. This is what we call as the joint PDF. So now we do not call a PDF, a probability density function, but we start talking about the joint PDF. Pxy, x comma y basically represents some sort of a probability, but for x intersection y, which means if I want to convert it into probability, then what am I supposed to write? So if I want to write down the probability of finding something in x and x plus dx and y and y plus dy, then how will it be related with the joint PDF? So it should be
So
PDF
del
Pxy xy. Yes.
dx, it should be del p by del x dx.
Dy. That's it. Remember that it is the probability density function which is given, and now you want to relate it with probability. So what were you doing earlier? You can think about it something like this. For example, that you have now two of those axes and your probability is something like this. So whenever you are taking this probability at any point, so this is something like making a small rectangular point x and x plus dx and y plus dy. So it is the intersection of this which gives you the joint probability. So we get what we call as the joint probability density function, which represents the probability of, let's say, finding a particle in the position x and x plus dx and y plus dy by this pxy xy times dx dy. You just compare it with one dimensional, it is a rather simple extension. However, we have to realize that it is a two-dimensional one, and that's why I am writing this capital XY. And there are other reasons also. Now, what properties will this PDF obey? What properties? Pxy should obey. One, that it should lie between 0 and 1, just like the PDF, what the PDF does. And what will be the normalization condition for this Pxy? This should be multiplied by dx dy. This makes probability, and then integrated from minus infinity to infinity in x, minus infinity to infinity in y, and this will give you 1. So PDF is just like PDF, the way you remember it. It is now what we call the joint PDF, as there are two random variables which are involved. So if I want to write CDF, which should be f of xy now. So how should we write this?
Integration from minus infinity to y, integration of minus infinity to x.
Right? And then just like the way you remember it, pxy xy dx dy. So it's an extension of our univariate analysis. Now something which is important to note, which happens for bivariate and multivariate further, but not in the case of the univariate ones, what we call as the marginal PDF. Now what are the marginal PDFs? If you take the projection of this joint PDF onto one axis, so if you take it onto, let's say, x axis only, so you will get what we call as the joint PDF of x, and now I write capital X here. This you get by taking the joint PDF xy and integrating over all y's. So this is what we call as the joint marginal PDF of x. And we can also build the marginal PDF of a given random variable y. This we can build by doing minus infinity to infinity pxy xy, and of course now integrating over x. Now if you look at these marginal PDFs, they will also obey exactly the laws of our probability, that it will be between 0 and 1 and minus infinity to infinity pxx dx is equal to 1, and so is for y's. So what we are getting basically, marginal PDFs, they are the univariate PDFs which are built from the joint PDF. And how do we build it? It is just by taking the projection onto a given axis. So that means that you are integrating over the other axis. If you want to take the marginal PDF on x, then you are integrating over y. If you want to take the marginal PDF of y, then you are integrating over x. And all the laws of the probabilities will be followed by these marginal PDFs. It's by construction. Yeah. So this is something which was not there earlier. I mean, in one sense, what you can think of, the univariate PDF is a marginal PDF. Some sense you can think of. There was no correspondence to the joint PDF in that case. And why bivariate becomes so important, that if I do the trivariate one also, then I can talk about p, x, y, z, and then I integrate over two variables dy and dz, then I get the marginal PDF of x, so on and so forth. Okay, so let's continue to build. One point which you found very important, maybe this is my point 3. What about if the two random variables are independent? If the two events A and B are independent, how do we define that? The events A and B. This is what we did in probability primer. So what does that mean? Do
The
you remember?
probability of one does not affect the other.
Which yeah, but that means the definition was P intersection B is equal to 0.
PA into PB.
PA into PB, not 0. 0 comes only in the case of mutually exclusive, not independent ones. Yeah. So what if the two random variables, remember that the random variable is nothing but some sort of a numerical values we assign to each of the sample point. If two random variables are independent, then our joint PDF PXY is written in terms of the marginal PDF product. Now this is something which you should now remember. You remembered it in case of the events, and now we would like you to remember this for the random variables. How do we define if the two random variables are independent? The definition is that joint PDF can be written as the product of the marginal PDF. So this is the definition. It's basically coming exactly from the place where you were getting your probability. So A intersection B is what you are getting for X comma Y, and PA and PB are nothing but the marginal PDFs. Okay, let's define expectation value of the random variable X. So how can we define that? This is again, I mean, it's following the same rule. So it should be X times PXY xy dx dy, and then integrating over minus infinity to infinity, minus infinity to infinity. What about EY, expectation value? Y, this will be, okay, minus infinity to infinity, minus infinity to infinity, y pxy xy dx dy. What about expectation value of X plus Y? This should be equal
The
to
sum of the two, mu x and mu y.
EX plus EY, right? Sum of the two. Now see an important point, that when I'm taking the expectation value of the sum of the random variable, it can always be written as the sum of the two. It doesn't matter whether X and Y are independent or not. Why I am saying it, this will become clear in my subsequent sections. But note here that Ex plus Y, two random variable if they are given, the sum can always be written at the expectation value. It's the expectation value of the sums. So simple. If X and Y are independent, then what is the expression of Ex becomes? What will be mu x? This will become minus infinity to infinity. Let's just write down minus infinity to infinity x times, and then how can we write this pxy xy?
Px into Py.
Right, px into py. We cannot do all the time unless until the random variable are independent. Dx dy. Can you further reduce it?
Yes,
What
sir.
will be?
अगर
We
हम
could
Yeah,
we could separate the integrations.
you can separate it, particularly if you look at y minus infinity to infinity py dy. What will be that?
1.
1. So you are left with minus infinity to infinity x pxx dx. Now look at this. This form looks pretty similar to what we did in the case of univariate one. If the two random variable x and y are independent, it doesn't even matter what is the PDF of y. It's the PDF of x, the marginal PDF of x, which will still be able to give you the mean or the expectation value. However, if x and y are not independent, please ensure that you are using your expression properly. Okay, I mean, then you can write EY also if x and y are independent. So I should somewhere mention here also independent. Okay, what will be EY in that case? XY independent?
So it will be minus infinity to infinity integration y p y dy.
Absolutely right. So great. Things look absolutely fine in terms of EX and EY. It doesn't look that complicated. The complication comes a little bit in terms of the variances. So variance of X, which we define as sigma X square, X expectation value of this. Now, definition wise, looks rather simple. X minus mu X square Pxy xy dx dy, and I should be integrating this variance of X. Variance of Y, that is also simple. Sigma Y square, expectation value of Y minus mu Y square, and you can write down minus infinity to infinity, minus infinity to infinity, Pxy xy dx dy. So up to this point, it is absolutely fine, doesn't look anything complicated. But what happens that when there are two random variables, we are interested in knowing if one random variable is correlated with another or not, whether X is correlated with Y or not. And then there comes a definition of covariance of X and Y. Now, this is a definition, so you have to just remember. Now, covariance xy is written as this, covariance xy or sigma xy. You may find that some books are writing it as sigma square xy, but it is the notation. I generally choose sigma xy. And this is how this will be defined: expectation value of x minus mu x times y minus mu y. So this guy becomes minus infinity to infinity, minus infinity to infinity, x minus mu x, y minus mu y, pxy, dy. So this looks rather lengthy, but this does not have any counterpart in the one-dimensional univariate one. So this is something what we are trying to figure out, if one random variable is correlated with other one or not. Now, first thing, in the case of variance X or a variance Y, I hope you remember that this guy can be written as E of X square minus of EX. This is what we wrote when we were doing the univariate one. Try to expand covariance XY definition and try to write it in terms of something what we wrote here, expectation X square minus expectation X whole square. So expand the term by multiplying, and then of course simplify it in terms of the expectation value. So sigma xy then becomes what? Expectation value of first term xy minus x mu y minus y mu x. All minuses are fine or something wrong?
Sir, plus आएगा mu x mu y.
Which one? This one.
Mu x mu y पे.
Right. So what will this become? Since this is the expectation value, so you can of course expand it in terms of the first term exy. What is the second one? Expectation value of x times mu y. Mu y
Mu
is,
x mu y, sir.
so this becomes mu x mu y. What about the next one?
Mu y
This
becomes
is mu
Mu x
x
mu y.
and mu x mu y, right? And one of those of course cancel. I mean anyone will cancel because it is just the numbers. So this is written as EXY minus EX EY. So this is another form of the expression of covariance XY. In fact, now you can see an interesting point. If I write covariance XX, that is sigma XX, this will be what? E of x square minus, which is nothing but what we define as variance of x. So what we call as the variance of x is nothing but the covariance of the random variable with itself. That is what we define as variance x. But the covariance word is generalizing. Now that we are talking about the correlation of the two, we did use the word independent. We are now using the word correlation, and I am just going to highlight it soon, except for one point. What is covariance XY if x and y are independent? What will be this? Any guesses? What will be the covariance, the correlation between x and y, if the two random variables are independent?
0.
Okay, let's just see. So let's just write expectation value of xy. What is this guy? This guy is minus infinity to infinity, minus infinity to infinity, x time y, pxy, xy dx dy. Right? Now, pxy is generally a joint PDF and you cannot reduce it further. But if x and y are independent, then I can write down my pxy xy as pxx pyy, right? So your expression of expectation value of xy becomes minus infinity to infinity x times pxx dx minus infinity to infinity y times pyy dy, which is nothing but x times ey. So your expectation value of x times y becomes same as ex ey. What happens to the sigma xy in that case?
0.
Sigma xy is 0, and what we call as that the two random variables are uncorrelated. So let me just summarize what I said. If x and y are independent, that is pxy can be written in terms of px times py, then the covariance of the random variable 0. This is what I define as uncorrelated. So if x and y are independent, then x and y are uncorrelated. And what is the meaning of uncorrelated? That the covariance term comes out to be 0. So this implies. What about the vice versa? What if sigma xy is equal to 0? That is, they are uncorrelated. Does it mean that x and y are independent? Or no? So that's the question. Okay, guesses? So I gave a definition. Remember, when I'm saying that x and y are independent, I am saying that the joint PDF can be written as the product of the marginal PDFs. The next definition is that the covariance equal to 0 is what we call as the two random variables are uncorrelated. We have already seen that if x and y are independent, then x and y are also uncorrelated. That means the covariance is 0. What about the other? If in a problem that the covariance xy is 0, does it mean that x and y are independent random variables? So that's the question. Whether uncorrelation implies independence.
Yes, sir.
Okay, so I will give you this as the homework. This is pretty important for your almost all the experiments related with modern physics and wherever the errors are statistical. This is quite important to me. But I am not explaining it right now. It is just that it's a homework one.
Sir,
Answer like thinking about whether EXY will be equal to EX times EY only if PXY XY can be written in this form, or in some other case also it can become. Yes, go ahead.
no, sir, I was about to ask about that.
Okay. There is a word which we use actually, correlation coefficient, rho xy. Basically, it is constructed from the covariances and the variances, sigma xy divided by sigma x sigma y. Can somebody think of what we have done? It is covariance xy divided by square root of variance x, variance y. What have we tried to do here? I mean, we already had the covariance. Why are we using the word correlation coefficient? This coefficient is a dimensionless quantity. And this coefficient remains between -1 to +1. What if x and y are independent or uncorrelated? What is this coefficient?
Zero.
Rho xy?
Zero.
This is
1.
0. No, it is 0 because covariance is 0. Sigma xy is 0, right? On the other hand, if this rho xy is +1, then we say that the two random variables are completely positive correlated. So x and y are fully correlated positively. If rho xy is equal to -1, they are still fully correlated but negatively, which means that if x is going in up direction, then y is going in down direction. So when we are having rho xy is equal to -1, rho xy is equal to +1, if x is increasing, then y will also be correspondingly increasing. In between -1 and 1, what we get is partial correlation, that x and y are correlated but may not be completely correlated. So this coefficient, correlation coefficient, which makes these covariances independent of any unit or the dimensionless one, this is a very common quantity to figure out how the two random variables are correlated. Since the covariance is a dimension, is a quantity having dimension, so you may not be able to appreciate the different covariances which you find out in variety of problems, but they can all be brought back onto the same footing if you convert it into this coefficient rho xy. And then figuring out if rho xy equal to 0, +1 and -1. In fact, a very common question which is asked, that how this rho xy plot, a scatter plot, looks like in the x versus y dimension space for the three cases, 0, plus and -1, and the cases in between. So why it is important? Because people, if they just gather the data and plot rho xy, which is built from this one, just by looking at that plot, one can infer if the random variables they are studying, they are correlated or not. For example, people living in the cities, people are educated. I mean, these two are two important, or or illiterate, let's say not educated word, but the illiterate word. So you can try to figure out, take the data, convert the variances and the covariances in terms of rho xy and plot it in this rho xy plot. Figure out, and you can figure out from that whether these two, staying in cities and being literate, they are positively correlated or not. So homework number 2 which I am giving for today's class, this was homework number 1, this is homework number 2, that try to find out the structure of this rho xy or the form of this rho xy for different cases when x and y are correlated in different manner. Fine. And we will discuss about the plots. These plots will be very useful in future when some of you might be doing research and there you are interested in figuring out if the two random variables you are studied are uncorrelated or not. One question I can immediately ask: you take the number of counts in the counting statistics experiment using a source and you take the background count without using the source. If somebody asks if N1 and NB are correlated or independent, how would you answer this question? N1 is randomly distributed. That's of course from the source. So it's a Poisson distribution. NB is also randomly distributed. But the background is coming from variety of sources, maybe cosmic rays, maybe the walls, maybe something else, the atmosphere. So how will you figure out whether the two random variables in your problem, they are uncorrelated or not? Because what I will be showing now subsequently, your analysis depends upon whether the variables are correlated or uncorrelated. And I will come to that. So questions up to this point, what we are doing. I just basically brought all the ingredients together. So taking cue from what we did in the case of univariate, we are just coming up with the idea of the bivariate distribution. Here we talk about the joint PDF. We can build our marginal PDF from the joint ones. That means that the univariate PDFs from the joint PDF, just by projecting the joint PDF onto a given axis, X or Y. PDFs will always follow the rules of the PDFs, be it joint PDF or be it a marginal PDF. Then we discuss certain things about X and Y being independent, the definition first, EX and EY. I wrote then EX plus Y can be written as EX plus EY, independent of whether X and Y are independent or not. Now, this why I wrote this, because EXY can be written equal to EX times EY. That is, the product of the random variable can be written in terms of the individual products only if X and Y are uncorrelated, or in this case X and Y are independent. You cannot write EXY is equal to EX-EY all the time, whereas EX plus Y is always equal to EX plus EY. So this is something which we read. And then the covariance. So without going into the further details, let me just share with you the quantity which we need to build when X and Y are not independent or are not uncorrelated. There we build a matrix called covariance variance matrix. People also call it error matrix. And for the two random variable, look into it how easy it is. What we do is something like covariance xy, covariance yx, covariance yy, which is basically writing sigma square x, sigma square y as the diagonal term, sigma xy as the cross diagonal term. Now, by the definition, covariance xy, is it same as covariance yx? Is it same or not?
Sir,
Covariance
same
Yes,
same
sir,
ही होना
same.
चाहिए
It's
sir.
same.
same here,
Same.
सही बात है, same है, whether you write EYX minus EYEX or whether you write EXY minus EXEY, they are basically identical. So the sigma YX is nothing but sigma XY. And immediately you will say, hold on, sir. We did not use any error matrix, even though we have used two random variables. Just for example, the example which I gave, where N1 is the count for the source, NB is the count from the background, both of which are random variable, we never used any error matrix like this. So what are we talking about here? And I will come to that. Just wait. Fine. So questions up to this point. Yes, no? Okay, so we just collected certain information regarding the bivariate one. Why bivariant play an important role? Because this covariance quantity, which is correlation between x and y, or the independence of the events which is there between x and y, you can extend it to multivariate ones. Whether x, y, and z, if three random variables are given. If x is independent of y, if x is independent of z, if y is independent of z, things like that. Or covariance of x with y, covariance of x with z, covariance of y with z. Those things are further extended. So for example, this is 2 by 2 matrix for two random variable. If there were three random variable, I would have extended it to 3 by 3, and I would be talking about sigma x square, sigma y square, and sigma z square on the diagonal ones, sigma xy, sigma xz, sigma yz on the off diagonal ones. And since it's symmetric, so it will just be that. So extending from bivariate to multivariate is rather simple. Okay. Let's do something which is z is equal to x plus y. Let's say we have a random variable which is the sum of the two random variable. Two random variable. We already know if I find Ez, this is nothing but Ex plus Ey. So writing mu z is rather simple. This is nothing but mu x plus mu y. What is variance of z? How to find it? Z minus Ez square. Fine. So I can expand it. Z is what? X plus y. Ez is what? Ex and Ey square. Then you do what? Then you collect the term x minus Ex together plus y minus Ey together. That's it. And use this as the first term, use this as the second term, open this bracket. Ex minus Ex square plus Ey minus Ey square, and then what? When you are opening the bracket with this as the first term, this as the second term. First term is this.
Sir,
Second.
2 sigma xy.
So rather than that, let me just write down. Yeah, I mean what you said is absolutely right. X minus Ex, y minus Ey, and 2 out I can take out. It's a constant. So let's look at sigma x square plus sigma y square plus 2. Look at the definition. This is nothing but 2 sigma xy. So if there are random variable x plus y, and I ask you to give me the variance of z, which is nothing but the sum of the two random variable, this will come out to this. What if z is equal to x minus y? What will be variance of z? Can you think about it now? Quickly do this. If z is equal to x minus y.
Sir, minus 2 sigma xy.
So whole expression would be what?
Sir, sigma x square plus sigma y square minus 2xy.
Minus 2 sigma xy.
Mm.
Fine. Now let me just correlate with what you have been doing in that counting statistics. Remember the expression what you were using. You are using counts from the signal, and then you remove the background count, and let's say you are building a quantity like n minus nb. I am writing n1 minus nb, but it is n1 be the counts coming from the source, which is random variable, nb is the background count, which is a random variable. So I build n prime from that. If I am asked to use this expression sigma square n prime, then what should be the result? The error in this sigma square n prime. So you got the error in sigma n1 and you get the error in nb. So how do you write it? Sigma square n1, that is my first random variable, plus sigma square nb, that is my second random variable. And then there should have been sigma n1 and b. Only if N1 and NB are uncorrelated, there or N1 and NB are independent, then you can write down this to be this. And I'm pretty sure that those who are doing in nuclear physics experiment, they can correlate with this expression sigma n1 square plus sigma nb square, that if you want to find out the error in n prime, then that is equal to the error square coming from n1, error square coming from nb, and taking the square root of that. You do not consider this term sigma n1 nb, because you are saying that n1 and nb are uncorrelated. But in general, in case if there are two random variable, one does need to figure out if they are really uncorrelated or independent or not. If they are not, then you see that the term sigma n1 nb is also coming up in the experimental errors. You cannot neglect it. And that's why on the previous page, when I said that we build what we call as the error matrix, which is a symmetric matrix. So you do need sigma x square, sigma y square, and sigma xy also, so that you know the complete picture of the error whenever you are constructing any quantities from those two random variable x and y. So knowledge of x and y, the sigma x square and sigma y square, that is sufficient only if x and y are independent. If they are not, then you have to consider the term which is coming up from this. And in fact, you can even appreciate that whether z is equal to x plus y or whether z is equal to x minus y, the first two terms are just adding up, sigma x square plus sigma y square in both the cases. It is the covariance term which will decide if the error will be lesser or more depending on what the covariance is. It can be minus, plus, anything, whether this is this or that in x plus y versus x minus y. If the random variables are independent, then you see that sigma x square plus sigma y square remains same from both z is equal to x plus y and x minus y. Questions here? So the whole idea of this error analysis, doing random variables and then thinking about how they are used, they are of immense use to those who are performing experiments. And since in MSc we have been performing experiments, even if we are interested in theory, that means that one place where probability and statistics can be immediately applied is the place where we are doing experiment. Another place, of course, is quantum mechanics. Another place is also, of course, is statistical mechanics, be it classical statistical or the quantum statistical mechanics, both the cases. So in certain cases, these are getting useful just like that. Those of you who are going to take, for example, electronics, you will find the whole idea of the digital signal processing is nothing but the application of this probability statistics. So I mean, you go wherever, you will find out that you are dealing with one in one way or other with this probability and statistics. it's quite possible that you might not be knowing, without knowing you are implementing. For example, students are implementing these errors just like that, and m prime is equal to n1 minus nb, and they are just using this expression just like that. So there they are using root n1 square plus root nb square, something like this. They are been using it without recognizing that they are coming directly from the idea of the bivariate distribution. Okay, it is 11 a.m. Questions? So what I will suggest, that try to go back, just take book, the Shom series book of the random variable, or pick up your Arfkin. Try to see the bivariate distribution and do any question on it. For a given p x y x y, find out various quantities. That means the marginal PDFs, the expectation values, the variances, the covariances, in order to just play with that. It's mainly about the integration or summation. So I'm not giving it here, but I'm pretty sure that in the tutorial we are going to give you certain more examples. Fine. And what we have coming up next is what we call as, just like we did the transformation of 1D random variable, we will do transformation of two-dimensional random variable. So given x, y, we will try to see, okay, let me just define the problem and we will do this problem next week. So given x, y and p x, y, that means you have the random variable and the joint PDF. If you know your z, another random variable which is related with these two random variables z and w, figure out what will be the PDF of. So given PDF of x and y, and given the relations of z and w with x and y, find out the joint PDF of zw. In fact, you will be able to do more. You can even find out the marginal ones by integrating over the corresponding variables. So that's what we are going to do next, which fall under the category of 2D transformation of random variable. We will do it next week. Any other questions? Okay, so take time to go through the slides or the notes which I have given and try to do an example. In case if you are not doing an example, just ask for me. I will just give you certain distributions. Okay, good. So thank you guys.
Thank you, sir.
Okay, sir.